What we're going to do now is we're going to continue our conversation on organic groups. And we're going to focus on proteins. Now, proteins are the most abundant organic compound in the body. By far. And what they are composed of, a large protein, is just a chain of smaller components called amino acids. And amino acids are nothing more than carbon, hydrogen, oxygen, and nitrogen. Okay, that's what they are. What proteins do in the body is very varied. Very varied. Okay? There are support proteins, the functions. Support. Okay, these are called structural proteins. Structural proteins. Okay. Movement. Okay. These are called contractile proteins. And you're going to know two of them very intimately when we start talking about muscles: actin and myosin. So support, movement. Okay. There are transport. Okay, they're called transport proteins. They're buffers. You can have proteins in a buffering system. Metabolic regulation. We call these enzymes. Okay. Coordination and control. And then defense. They are immunoglobulins. You've heard of things like IgA, IgE, IgD. Those are all small proteins. Well, they're not actually small. They're actually large proteins that are built by the immune system to help protect us from foreign invaders. Okay? So proteins, they're made from amino acids, chains of amino acids. Okay? Amino acids are just built from the big four: carbon, hydrogen, oxygen, and nitrogen. Okay, and they have several functions: support, movement, transport, buffers, metabolic regulation, control and coordination, and defense. So let's take a look at an amino acid. Let's look at the general structure of an amino acid. We're going to say AA for amino acid. Okay, so if we look at it, okay. This is an amino acid. Okay, so the first thing you should notice when you look at an amino acid is here. You've seen this before. This is the carboxyl group. Okay, and if you remember from fatty acids, that what's going to happen physiologically is we're going to get rid of this. So it's a proton donor. That's what makes it the acid, this carboxyl group. So that's the carboxyl group. Okay. All amino acids are built around this carbon right here. And it has been named the central carbon. I know, what a name. What a name. Okay. And then here in blue, we have this nitrogen bound to two hydrogens. This is called the amino group. So if you look at amino group and you look at carboxyl group, we have amino carboxyl acid. Amino acid. This is where we get the name amino. We get the carboxyl group that gives us the acid. The acid. Okay. Of particular note, as you see here, R. The R. Now the R here doesn't mean an element or anything like that. Okay. R is the functional group. This is the functional group. Not functional. Okay. This determines the type of amino acid that we are dealing with. Okay, so if I change the atoms that are in the R group, that's going to change the amino acid. It's going to make some amino acids are hydrophilic because we have a different R group. Some amino acids are going to be hydrophobic because we have a different R group. Okay, amino acids are going to fold in a weird way because of the way, what the R groups are. So the R group is what changes the function and properties of an amino acid. Now there are about 20 different R groups, which means that there are about 20 different amino acids. You don't have to remember them all. It's not important. You just have to know that that's the thing that changes. Everything else about an amino acid here is the same. All amino acids have an amino group. All amino acids have a central carbon. All amino acids have a carboxyl group. All amino acids have an R group. And finally, all amino acids, if you want to get really nitpicky about it, have this H, which is the hydrogen attached to the central carbon. Okay, so that's it. So now how do we make a protein? How do we make a protein? It's actually quite simple. If I want to make a large protein, there's only one reaction that the body will use to make things larger, and that is a dehydration synthesis. So we're going to show you a dehydration synthesis. So what we're going to do is we're going to draw an amino acid here. So we're going to draw one amino acid. So we got an amino group, central carbon, our functional group or random group, and our carboxyl. All right, so now we've done this several times. You should be able to say, okay, hey, this is going to be the reactive part of this molecule, and it will be. Okay, that hydroxyl group is reactive. So in order to make a protein, I'm just going to string several amino acids together. So what I'm going to do is I'm going to have another amino acid coming up right next to it, central carbon, functional group, and our hydroxyl group. Hydroxyl group right there. So in order to get these two together, I've got to take off this OH, which is a hydroxyl group, and then I have to take off that hydrogen. And then what is that going to do? It's going to make water. So I'm going to pull off that water. And what is it going to do then? So what it's going to do is it's going to combine them. I'm going to have the first amino acid here, central carbon, hydrogen attached to it, functional group, carboxyl group, and then I'm going to bind directly to the nitrogen of the second amino acid, central carbon, the hydrogen, the functional group, and then the carboxyl group at the end. All right. So here, right here, actually draw it in a different color so it makes more sense. Right here, it's this. It's right here. I basically combined those together. And what this is called, this bond between this carbon and this nitrogen, it is called a peptide bond. It is called a peptide bond. All proteins are held together by peptide bonds. And all a peptide bond is, it is the bond between the carboxyl group of one amino acid and the amino group of another amino acid. So what you do is, if you want to make a protein, all you do is you just chain these amino acids one after another, after another, after another, after another. And that's how you make your protein. That's it. It's no more complex than that right there. Okay, if I want to make a protein, just chain the amino acids together. And that's what your body does. Your body just doesn't have preformed proteins. Okay, it has to make the proteins that it needs. And what does it do? It goes and gets the amino acid stores and it builds the proteins as it's told to build them. Okay, and it does it just like this, through a simple dehydration synthesis. And that's what this is, dehydration synthesis. Okay, and what that's going to do is it's going to pull off this water to bring the two amino acids together and form a peptide bond. Okay, that's it. Now, when I've done that, the structure of proteins, when I string these amino acids together, that's called the primary structure. That is the primary structure. The primary. And that is simply the sequence of amino acids. That is the primary structure. So if I have AA1 bound to AA2, bound to AA3, bound to AA4, bound to AA5. That is the primary structure of my protein. Okay? Now, when you have this chain, it doesn't exist in a vacuum. Okay, it's usually floating in some kind of fluid. Okay, and when you have it floating in some kind of fluid, these side chains, remember those R's, what they're going to do is they're going to start interacting with each other. They're going to start pushing each other away, or they're going to start pulling each other closer. And what that is going to do is it's going to fold the protein. The protein is going to take on a new shape. And what that is called secondary structure. Secondary. Okay, that is a secondary shape. And what that is hydrogen bond interactions will cause bonds to form, alpha helices. This means alpha helices, or beta, that's beta pleated sheets. So now what an alpha helices is if I have my string of amino acids, I'm just going to draw a straight line. Okay, so say this is my string of amino acids. So this is primary, one with a little zero next to it, like that, that's primary. Now if this starts to curl on itself and it starts to wrap like this, like a phone cord, okay, that's called the alpha helix. That's called the alpha helix. If that primary structure instead starts to do this, starts to curl on itself like this, that's called a beta pleated sheet. Okay. Now the thing about this is everybody assumes, oh, one protein can only do one thing. That's not necessarily the case. You can have alpha helices turn into beta pleated sheets, go back into alpha helices, It all just depends on how the amino acids are actually going to interact with each other. Okay, so that's what it is. So that's primary and that is secondary structure. Now, we're going to continue folding. We continue folding because it can't be easy. It can't be easy. Okay, so then we have what's called tertiary structure. And what this is the protein starts to fold in on itself and make like a glob, and it's called globular. So if I have this, if I have this, let's say I have my alpha helix, and it turns into a bladed pleated sheet right next to it, and it turns into an alpha helix again, and a beta pleated sheet here, and an alpha helix out here, and a beta pleated sheet out here. Beta pleated sheet in this direction and alpha helix in this way. You see, it's just become this jumble, as it basically looked like I scribbled on it, and that's globular. Okay, that's further folding. Okay, and that happens, and all it is again, it's as you fold the protein, more hydrogen bond interactions and intermolecular stresses cause it to fold again. Okay, and that's this further folding is the tertiary. Then we have one final fold, and this is called the quaternary. And this is when you have several individual strands coming together to make a full-fledged protein. So this is the final form, and it's several proteins making a larger protein. Okay, so for example, let's say I have my one protein that's got beta pleated sheets in several directions. This way, it's got some alpha helixes here. So that's my one protein. Now let's say that there's another protein that comes in and its alpha helixes here and beta pleated sheets here, and they kind of wrap around each other. That is the quaternary form. An example of this would be hemoglobin. Hemoglobin is a protein that has a very distinct quaternary form. It's got 4 individual strands, 2 alpha strands and 2 beta strands, and they form a large globular protein that is just meant to carry oxygen and carbon dioxide. Okay, so we've already, how far along? Okay, we're at 20 minutes, so I'm going to stop it here, and I'm going to talk more about a special protein called an enzyme in the next one, but I just don't want to make this like 40 minutes long. So that's enough for this one.